All right, so in this lesson we're going to be talking about section 6.7, which is the systems of linear equations in two variables. It is the last algebra kind of section that we cover, so it'll finish up this unit or this module that we're currently in. All right, so 6.7, if you have your notes, print those off of the attachments and follow along. We're going to talk about just some definitions first of all, some words to write down here. So if you have number one, if you have two or more linear equations that involve the same variables, that is called a system. So number one is system of linear equations. The name of the section. A system is more than one, two or more linear equations. Number two, a solution of a system of linear equations is an ordered pair that is a solution of both equations. So the solution is the point or the ordered pair that works for both equations or all the equations in the system. So both. Number three, the ordered pair that is a solution of two or more linear equations is called a consistent solution. We call that a consistent system of equations, so there's just that one solution where they cross. Consistent. Okay, number four. Number four says determine if the ordered pair 3, 4 is a solution to this system. So notice we have, there's one linear equation like we graphed in the last section, and then we have another linear equation making a system. So if this solution solves, there's only one point that will work for the x and the y. A consistent system only has one solution. So is this it, is the question. We're going to find out how do you figure out that point shortly. But just look, see if it works for both. See if the lighting is better there. Okay, so we're putting in the 3 is the x value, the 4 is the y value, and we're seeing if it works for both of these equations. So the question is, x is 3, y is 4, is 2 times 3 plus 5 times 4 equal to 26. And think about that for a little bit, and you'll see that it is so. 2 times 3, that would be 6, plus 5 times 4 for y, that would be 20. That works. So it checks out for that equation, but to be the solution to the system, it has to work for both. So we have to plug it in the next one. Is 4 times 3 for x minus 2 times 4 for y equal to 4. So that's 12 minus 8, and there it is. So yes, I would say that is the solution to that system. And that's ultimately all we're doing on this section is we're looking for the point that solves both equations. Now some of you all that kind of think, do math in your head, which not me, but if you're able just to think about these, and sometimes you can just come up with the answer. Try to find the number that makes both of these equations true. That is our goal in this lesson. We have some strategies for doing that though, you know, like we always do. We have some math strategies that will get us there, some formulas, step-by-step ways. All right, number 5. We're going to draw number 5. On number 5, if a system of linear equations is represented graphically, the graph will be a pair of straight lines that can be related in the following ways. You know, these are linear equations like we graphed in 6.6, so they graph to be straight, right? They're going to be straight line. So maybe we'll have a line and another line going opposite ways, and those lines will cross. That points the solution. If they're crossing, they'll just cross in one place. So that's what we're looking at in A part. So draw a picture of that. Well, that won't work. I'm having marker issues, guys. Okay, so a picture of that. So it could be anything because we don't have the particular equation. So there's no wrong answer. Just draw 2 lines that cross in a point. So you've got some sort of equation, and anytime you've got 2 lines that aren't parallel, they'll eventually cross each other. So as long as the lines aren't parallel, they're going to run into each other eventually. So that's the first situation. So draw an example. If there is one solution, the lines cross, or intersect, I guess is the better word there. Intersect in one point. Okay, B. If there are infinite solutions, the lines are dependent, is the word here, dependent. If there's infinite solutions, so what could happen, and sometimes you can't always tell this just right up front looking at the equations, but they're really just the same equation. We draw one of the lines And then you look at the next equation, and it's some reiteration of that, some equivalent equation, maybe multiplied through by something, or it's in a different order. It's not in standard form and you don't recognize it. But then when you get down to it in graphing form, it's exactly the same line. So if the line lies right on top of the other line, they're the same line basically. We call that a dependent system. And again, you might want to know that means they're the same line, or a line on top of a line. And so the solution is where they cross. So if they're on top of one another, they're crossing in infinite places. Every point coincides. So we'd say they're crossing or intersecting everywhere along that line, or infinite places. So a dependent, where they're just the same line, is kind of a special case where there's infinite solutions. So if two lines have the same slant on them, the same y-intercept, if you would solve them each for y and use that graphing method we talked about, and you notice you get them set up, y equals the mx plus b form, and they're just exactly the same slope and intercept. You don't have to do anything. You can stop and say, oh, these are just the same line. There's going to be infinite solutions, so you can answer it without having to proceed. Then the third scenario, C, is if there's no solution. So think about what would make a no solution situation. The solution's where the lines cross. So the first example, they cross in one place. If they're not parallel, they run into each other. The second scenario, they're the same line on top of one another. The third scenario then would be they're parallel. They're two lines running parallel to one another. So maybe like this line, so we're drawing this on your notes, and then another line. You don't have to have my exact two parallel lines. Yours may have been running this way, but just draw a scenario where you got two lines running parallel. They have the same slope, same slant on them, but they're intersecting the y-axis in different places. So they're unique, different lines. So they're parallel lines. Parallel lines will have no solution. This is our no solution symbol. So it says if there's no solution, the lines are parallel. Should go in that space. And then draw your example, please, there. All right, so on the next page, we're going to talk about how do we find these solutions? How do we come up with it? Without just kind of thinking off the top of our head, let's talk about a method for finding the solution to a system. All right, so page 2. We have actually 3 methods to solve these systems. I guess 4 if you just try to think it up. You could consider that a method, I suppose. But as far as real methods techniques to work, the first method is we graph each line. Just